Welcome my friends, welcome to my next lecture. Now I am still in the process of review of complex numbers and its algebra and topology of sets. So I have discussed complex numbers and its algebra and couple of its nth roots of unity and so on and so forth. So now I am in the middle of the discussions of topology of sets. So couple of concepts I have already discussed. So today my plan is to finish kind of couple of another concepts in topology of complex numbers, sets of complex numbers, and then I'll move my discussion to complex functions, and then I'll talk about the concept of limit, continuity and differentiability. Maybe differentiability I'll talk about in the second week, but my plan is to just finish limit and continuity, concept of limit continuity in week 1. Week 2 onwards, maybe I'll start with the notions of differentiability, then analyticity and so on and so forth. Okay, so as I said, so I have already discussed couple of concepts like open set, closed sets, closure, limit point or accumulation point. So this is once again, I just recall that arbitrary union of open set is open. Okay, finite intersections of open set is open. This is arbitrary union. Okay, this is finite intersections. Arbitrary intersections of closed set is again a closed sets, and finite union of closed set is a closed sets. So these are the properties, and those properties you are already familiar with in real analysis as well. Okay, now come to the concept of boundary point. Now the word boundary, you can guess something like, so what is the definition? Of course that part is okay, but mathematically what should I say? So mathematically I say that, okay, so first I need to discuss what is the definition of boundary point mathematically. Okay, so let me start with a set S, which is a subset of the complex plane. Then what is the complement of a set? It is nothing but that C minus S. That means you consider the set where S is not there. That means C minus S. That means all those points Z is in C such that Z is not an element in S. Okay, fine. Now what is the definition of boundary point? Now from the term boundary you can say that it is not in the inside of the set or in the outside, something like that. That means it is in the boundary. But that is like if you think in that way. But the point is that if I want to say what is the definitions, mathematical definitions of boundary point, then I have to say that yes, look, this is the definitions. A point Z0 is said to be a boundary point if every neighborhood of the point Z0, it should contain at least one point of the set and at least one point of the complement of the set. For example, so that is a mathematical definition. For example, if I consider this set mod Z is equal to 1, that means what? That means or say mod Z strictly less than 1, right? This is my set. So that means this is set is that set of all complex number whose modulus is strictly less than 1. That means this is the inside. Okay. For this set, I am saying that this is exactly equal to mod Z is equal to 1. That means the circle of radius 1 and center 0, 0 is the boundary of this set mod Z less than 1. Why? Because you see, if I take any point in this mod Z is equal to 1, and if I take any neighborhood, now how the neighborhood looks like, say I'm talking about open neighborhood, so it should be an open ball with center, so let it be my point Z0 with center Z0 and say some finite radius. Now if you see, whenever I will draw a small open ball or open disk around that point, then you see some point of the set is in that set mod Z is strictly less than 1, some point is there and some point from the outside is also there. That means if I take a point Z0 such that modulus of Z0 is equal to 1, then whatever neighborhood I can take around the point Z0, it contains, so for example, you have some portion here, you have some portion there. So this portion, it will contain some point from the set S, and this portion will contain some point from the S complement. So this is my S, and what is S complement? This is my S complement. So this kind of point is called what is called boundary point. So therefore mod Z is strictly less than 1. If I take this is my set, what is the boundary point? Mod Z is exactly equal to 1. Okay. So now our definition is clear. So a point Z0 is said to be a boundary point if every neighborhood in Z0 of Z0 should contains, see, at least one point in S and at least one point not in S. That means at least one point should lie in the complement of the set. Okay, so that is every neighborhood should intersects my set S and SC. So for example, this point, if I take the neighborhood, it intersects my S and it intersects my S complement. Okay, so I have written, so for example, each point on the circle mod Z is equal to 1 is a boundary of the set mod Z is strictly less than 1. Okay, this is a notation. The set of all boundary points is called the boundary set. of S, and it is denoted by either BD of S or delta of S. That is called the boundary of the set S. Okay, so boundary point I am done. So now next concept is that exterior point. Now what is interior point, you know? So interior point means is that if I have a set S, a point belongs to that set, it is an interior point if there exists a neighborhood around that point which should fully contain in my set. That is then I say that that point is an interior point. So exterior point means what? It is the complement of that. That means what? That means a point, I will say that is an exterior point of the set if there exists a neighborhood of that point which should fully contain in the complement of that set, not in the S but the complement. So that's what I have written. Look, a point Z0 is said to be an exterior point of the set if there is an open neighborhood in Z0 such that this is phi. Now this is phi means what? This is phi means I am saying that in Z0 fully contained in the S complement. So that means in Z0 should contain in S complement, and then I am saying that Z0 is an what is called exterior point of S, or you can say that Z0 is an interior point of the S complement. Anyway, it's up to you. Okay, so I'll say that Z0 is an exterior point of S if and only if Z0 is an interior point of the set S complement. Okay. Again, there is a notation. The set of all exterior point of S is called the exterior set of the set S, and it is denoted by EXT of S. So for example, if I consider this set, okay, if I consider mod Z is less than 1, so what is mod Z is less than 1? So this is my unit circle, so this is mod Z is exactly equal to 1, this one is mod Z is less than 1, and this is the one, it is actually mod Z is greater than 1. Now what is the exterior of the set mod Z is less than 1? This is actually the set mod Z is greater than 1. Why? Because if I take any point here, then I can always have a small open neighborhood or open neighborhood around the point Z0 or open disk which is fully contained in the set what is called mod Z strictly less than 1 complement. That means mod Z greater than 1, because whenever I take a point here, there should be a positive distance from the boundary, and you can always find an open ball with some center that point and a finite radius which is fully contained in the set mod Z is greater than 1, which is the complement of the set mod Z is strictly less than 1. So therefore each point is an interior point of the set mod Z is greater than 1, and therefore that set mod Z is greater than 1 is an exterior set of exterior points of the set mod Z is strictly less than 1. Okay, I hope this is clear. Say mod Z, so that means you can think about that. Say take a Z0 such that mod of Z0 is greater than 1. Now if mod of Z0 is greater than 1, that means it should be lie here, because this is the set where mod of Z is exactly equal to 1. Now mod of Z0 is strictly greater than 1 means it should lie here. That means there should be a positive distance from the set mod Z is exactly equal to 1, and then you can always have a small open ball around that point with finite radius fully contained in the set mod Z is greater than 1, which is the complement of the set mod Z is less than 1. So therefore the point Z0 which mod is greater than 1 is an exterior point of the set mod Z is less than 1. Okay, so this is a picture I have tried to draw. So for example, this is my set, the green one. Okay, so for example, this point, it is an exterior point. It is quite clear because this open neighborhood or open disk or open ball which is fully contained in the complement of the set. This is the complement of the set, na? Okay. Acha. This point is an interior point because this is the corresponding neighborhood which is fully contained in the set. That's the interior point. Acha, boundary point, this is the boundary point because whenever I take an open neighborhood or open ball, it contains some point of the set and it contains some point of the complement of the set. And limit point, so I just draw a picture. So as I said, so whatever neighborhood I can take, any neighborhood of this point, deleted neighborhood, if I take out this point, it should intersect my set at least one point. So there are plenty of points are there. So these are the points called limit points. So this is the picture. Pictorially you can think about, that's how the kind of definition. Geometrically you can think about, or pictorially you can think about that. This is the kind of scenario concerning the definitions of interior point, exterior point, boundary point and limit point. Another two concepts, this is called bounded set and compact set. So like bounded set, you know in real line what is the definition of bounded set. That means a set A subset of R, it is called bounded. You can say that, okay, if there exists a R positive such that you can say that mod X is less than R for all X in A, then I will say that my set A is bounded. That means what? That means this conditions will imply that A is fully contained in the interval minus R to R. Or you can say that it is open, whatever it is, you can take little more than R, then you can have it open. So that means what is the definition of bounded set in R? That means a set A in R real line, it is bounded. That means if I have a open ball or open interval which should fully contain my set A, open interval of maybe finite length, you can say. So you can have an open interval of finite length, and if it contains my set A, then I will say that A is bounded. Now same concept you can kind of extend in the context of complex plane. Why? Because open interval replaced by open ball or open unit disk, whatever it is, right? So same thing. So I am saying that our set S subset in the complex plane is said to be bounded if there exists an open ball. See, like open interval you can replace by open ball with some center Z0 and finite radius R0 such that my set should fully contain in that set. If a set S has this kind of properties, then I will say that my set is bounded. That is, S can be put inside an open ball with some center and finite radius. Like in the case of R, I can say that my set A is bounded if there exists a open interval of finite length which contains my set similarly. So suppose this is my set S, and you see I have this open ball with some center Z0 and finite radius which contains my set S, therefore my set S is what is called bounded. One observation that empty set is always bounded. A set which is not bounded, I will say that that set is unbounded. Okay. And what is the definition of compact sets? Now if you remember, what is the definition of compact set in R? A set is compact in R if and only if it is closed and bounded. So similarly, in the complex plane also I can have the similar kind of theorems or definitions. I can say that a set in the complex plane is said to be compact if and only if it is closed and bounded. Okay. So anyway, so their definitions, like you can say that in a real line we know that a compact set has a different kind of definition, like every open cover has a finite subcover. But then like Poljano versus theorem or like Heine-Borel theorem, I think I should say Heine-Borel theorem, that a set is compact in R if and only if it is closed and bounded. So that you can also think about as a definition. So both are equivalent. In the context of complex plane, I am saying that definition of a compact set in the complex plane if and only if it is closed and bounded. But when like in terms of topology, like that is same as every open cover of your set has a finite subcover. Both are same. Okay. So but for the timing, you assume that the a set subset of the complex plane is compact if and only if it is closed and bounded. Yes. Okay, so then another concept like connected set, domain and region. And domain and region I need it because later on when I'll talk about functions defined on a domain, now you can say that what do I mean by domain. Okay, so domain, so before that let me just talk about what is connected set. So connected set, of course I am kind of defining it in a more stronger way. Okay, so first I am defining what is polygonal path. What is polygonal path? See, look, let W1, W2, Wn plus 1 be n plus 1 points. You have a complex plane, in a complex plane, and let Lk denote the line segment joining the point Wk to Wk plus 1. Then the successive line segments L1, L2 up to Ln form a continuous chain known as the polygonal path, and that joins the point W1 to Wn plus 1. Okay, so that means I will say that suppose this is my W1, this is my W2, this is my say W3, then I am considering what is called line segment, right? So this is line segment, this is line segment. Right? So this kind of path I will say that is a polygonal path. Okay, so if I have n plus 1 points or n points, then from the point W1 to W2 you have a line segment, W2, W3 you have a line segment, W2, W3 to W4 you have another line segment. So this union like line segments, successive line segment, I will say that it is a path joining from the point W1 to the point W4. Okay. If I have this kind of concepts of polygonal path, then what is the definitions of what is called connected set? Connected set is that, okay, look, these are my definitions. An open set S in the complex plane, I am saying that it is connected if every pair of points Z1, Z2, so that means whenever I can take 2 points Z1, Z2 in S, can be joined by a polygonal path. I can join the point Z1 and Z2 via polygonal path, but what I demand is that that path should lie entirely in my set S. So that means, for example, look at this picture. Okay, so suppose this is my set. Okay, now if I take 2 points at W1 and W3, so now I am saying that if I join W1 and W3 by some polygonal path, and that path should fully lies inside that set, then I will say that that set is connected. And here it is the case. If I take two paths, then this is my polygonal path I am joining, and this path is fully contained in my set. So So that's why this kind of path set is called what is called connected set. Okay. So for example, if I take like say circle, say mod z is strictly less than 1. Is it connected? Well, you just look at the definition. So I am taking 2 points, say this is my z1, this is my z2, okay, and you can join. So so that means what? What is the definition? An open set. First of all, it is open. Okay, I already open ball or open disk of some center and radius. It is an open set. So it is an open set. Perfectly all right. It is connected. That means every pair. If I take any pair z1, z2 from that set, it can be joined by a polygonal path. Number one, and number two is that that polygonal path should fully lies entirely in that set. So let me just check with these properties. So this is my point, suppose 1 point z1, 1 point z2, and I have suppose this is the polygonal path. Okay, in fact you can take the straight line, not an issue, right? So this I can join z1, z2 by this kind of polygonal path, and this path is fully lined inside this set, so therefore this set is connected. Okay, so now look, but there is a note. Okay, what it says? It says that the concept of connecting any 2 points by a path is actually known as path connected, and path connected implies connected. Okay, so that means, as I said in my definitions, like the definitions of connected set, the way I have given the definitions, it is actually a stronger way. That means, though I am saying it is connected, but actually I am saying it is a path connected. That means I have a set, I am taking 2 points, and I say that, okay, join these 2 points by a polygonal path. So suppose this is my set, take 2 points z1 and 2 points z2, and I am joining by a polygonal path. And what I demand is that that path should be also lie inside that set. If it is true for any pair of points, then I will say that that set is connected. So what I am trying to say is that since I am talking about the joining 2 points by a polygonal path and demand that that polygonal path should fully lies inside that set, those kind of connectedness is called actually the path connected, which is more stronger property than connectedness. And so if I have a path connected, it is always a set is connected. So that's what. So even though I am saying it is a connected set, but the way I have defined, it is actually path connected, which is little stronger than the connected one. Okay, so if a set is connected, so this is one exercise maybe you can think about, that if a set S which is connected, that means in that definition the way I have given, then if I consider the closure of the set, that is also a connected set. Okay, so that's you can prove it as an exercise. So now you may ask that why it is like little stronger, because you see in the topology, like the kind of course topology course, if you have a first year master students or say advanced undergraduate students, those who have done a first course in topology, then there is a definitions of connected set, like arbitrary topological space, there is a definition of connected set. That means, so there is a like mathematical definitions. I am not kind of giving the appropriate definitions here, but you can think about that our set is connected, so you cannot write that set as like or maybe you can say I can say in this way. So a set is, suppose you have a topological space, so I am just very briefly I am saying, not the kind of proper A. So suppose this is my topological space, I will say that A subset of X which is connected. That means I cannot write my set S as union of two disjoint open sets such that whose intersections is phi. So I cannot have two non-empty disjoint open set such that I cannot write S as U1 union U2 such that U1 intersection U2 is first. I cannot write. If that is the case, then I will say that my set is S is connected. And if I can write that set as union of two disjoint non-empty sets, then my set S is called disconnected. So I'm not saying that definitions here. I am saying little stronger. What I am saying is that okay, I mind my definitions. Take a set as subset of the complex plane, then I will say that consider any 2 points, and if I join by a polygonal path and that path is fully lies inside that set, then I am saying that this set is connected, and path connectedness implies connectedness. But there is an equivalent criteria about path connected and connected. I am not discussing that, but for the timing, my definition is that the connectedness definition is that a set is called connected if I take any 2 points and if I join by a polygonal path, that polygonal path should fully lies inside that set. Okay, and this exercise you should do if a set is connected, then closure of the set is also connected, the way I have given the definitions. So this is kind of picture of connected sets and the kind of domain. What is that? So this is very important. I kind of sometimes or later on I use very frequently. Suppose let f be a function defined on a domain, then you should know what is domain. Okay, so in my kind of definition is that an open connected set, a subset of the complex plane, is called a domain. So domain means it is a subset, it is a set of the complex plane which is open and which is also connected. A domain together with some, none or all of its boundary points, it's called a region. Okay, so these two definitions you should know. So domain means I am talking about it is open and connected, and what is region? A domain, that means it is open and connected, but either you can include some, none or all of its boundary points. So this is one picture I have given. So this is a connected set. For example, if I have these 2 points, so suppose these 2 points, so I can go from this to this point to this point like this. So this is a polygonal path which is fully contained. If I take this point, so I can go there. So this is a connected set. Okay, a set that is not connected is called the disconnected set. For example, this is a disconnected set. This is a connected set, right? This is a connected set. Why? Because if I take these 2 points, so I can always join by a line or polygonal path which is fully contained. But if I take a set which is this union this, then it is disconnected. Why? Because if I take a point here, so I can join these 2 paths like this one, but this path which is fully not contained the union of this and this. So therefore this set is disconnected. Okay, so that means this is a connected set, this is a disconnected set. So I hope it is clear, because if I take 1 point here, I can join it by a polygonal path, but from the picture it is quite clear this portion will not be lying inside this union this. So therefore this is a disconnected set. Last concept, another concept, I should not say last concept, this is another concept, this is called convex set. What is convex set? I think most of you know. A set S is said to be convex if every straight line or line segment L joining any 2 points should lie entirely inside the set S. So therefore, for example, again you consider this set, mod z is less than 1. So this is my set. It is actually a convex set. What is the definition of convex set? You have a set S, take any 2 points, join these 2 points by a straight line, and I demand that straight line should also lie inside that set. And this is the case, because if I take a point here, say this is Z1, here Z2, then if I draw a line segment which is fully contained in that set. If I take another point here, the line segment fully contained in that set. So therefore this kind of set is what is called convex set. Now you can guess here. So if I have a convex set, so this is also I can think about as a polygonal path, because you have just only a straight line. So that means what is the definition of convex set? Is said there that if I take a set, if I take a 2 points, the line segment should fully lies inside that set, and that line segment I can think about as a polygonal path which has only one line, right? So therefore if I have a convex set, if I take 2 points, so the polygonal path also lies inside that set, so therefore that set is connected. That means convex set is connected. From there I can say, but the converse is not true. For example here, so this is a connected set, this is connected, this is connected, but it is not convex. Why this is connected? Because if I consider this point and this point, okay, so I can go there and come back here. So this is a polygonal path which is full lies inside that set, so therefore this is a connected set. But this is not convex. Why? Because if I take this point and this point, so I need to see whether the line segment joining these 2 points fully lies inside that set or not. Now draw a line. So this is the line segment between these 2 points, but this is the portion which is not lies inside the set. So therefore this set is not convex, but it is connected. Okay, so therefore convex set is again like very strong. So if I have a convex set, that means I demand that any 2 point, the line segment joining these 2 points should also lies inside that set. That means the path, polygonal path, here polygonal path means only the straight line, it is also lies inside the set. So therefore it is a connected set, but converse is not true. For example, this kind of set will have that 2 points which I join by polygonal path which is lies there, for example this, but the straight line is not fully contained because this portion is the outside of the set. So therefore this is a connected set but not convex set. Okay, so I think that's all about like what is called like the topology, review of complex number, like nth roots of unity, geometry of that. So all kind of stuff, very basics of complex numbers. Now I move my discussion to the another concept like functions. So like in real analysis, you started with the functions of real numbers or real variables with real valued functions. Similarly, now I have a complex blend. I know the definition of complex number, couple of its properties, its algebra, then the distance, topology, very basics, whatever I need in my course. So that kind of preliminaries you are familiar with. Now I move my discussion to the concept called functions. So what is functions? Okay, so this is complex functions. So you know what is real function. So that means I have a function shape, it will have a domain, it will have a range. From each point domain, it should map to a definite point. So same thing here. So a complex valued functions f of a complex variable is a rule that assigns to each complex number z in the set D subset of C to one and only complex value w. So that means if I have a function f D subset of C to C, it says that if I consider a point z in D, it should map to a definite value one and only. So I am saying that this is f of z or w. So this kind of object or rule is called the functions, and I am writing w is equal to f of z, which is the value of the functions f at the point z. I am writing at w, then I am saying that w is the image object under f. So like kind of standard notations you know in the context of real number as well. Okay, so a complex valued functions f of a complex variable is a rule that assigns to each complex number z in the domain to one and only one complex value in the range, and I am writing w is equal to fz. W is called the image of f, image object under the map f. Okay, so and look, the set D is called the domain of the definition of my function f. The set all those w's f of z, where z running over the domain, is called the range of f. So these are the kind of standard notions in the in the context of functions, whether it is real variable or complex variable. Okay, in real variable I am dealing with real valued functions with real variable. That means domain should be a subset of real number, range should be a subset of real number. But whenever I am talking about complex valued functions with complex variable, same rule or same definition will be there, but this time your domain should be a subset of complex number, range will also should be a subset of complex number. Okay. Now look, usually the real and imaginary part, that is very important. So this discussion is very important later on. Why? Now look, so usually the real and imaginary parts of z, generally I will denote by x and y. That means z is equal to x plus iy or x comma y, whatever it is. And those of the image point, that means the image object under the map A, I will denote that by u and v. So that means w I will write u plus ib. Okay, respectively, so that w, as I said, w is equal to f of z, which is u plus ib, where now u can be written as u object, which is a function of x and y, v is v object, and which is a function of v of x, y, are real valued functions of z. So therefore what is very important is that if I have a complex valued functions of complex variable, then that functions f I can write of the form u plus iv, where u is a real valued functions of real variables, or u is a real valued functions of complex variable, and v is a real valued functions of complex variable, or v is a real valued functions of real variables. You can think in that way. So why? Because this is very nice, because you see, this is my map, I can say that, okay, let me remove this part. Okay, so now f is a map from D subset of C to C, right? What is that map? So z goes to f of z, and which is w. Now you see, as I said, in the domain, if I take a point z in D, then I am always have the notation it is of the form x plus iy, and in the range, if I have a fz is equal to w, it is of the form u plus ib. Okay. Now look, so if I therefore if I change z, then my value f of z will change, that means my w will change, that means my u and v will change. So therefore I can think about u will change if I change my z, v will change if I change my z, and when z will change if I change my x and y. So therefore in conclusion I can say that u will change, which is a real valued because it's a real part of w, if I change my x and y. Similarly v will, which is also a like imaginary part of w, so that is also real valued, but it will change if I change my z in terms of in other words, if I change my point x and y. So therefore I can say that I can write my f of z as u plus iv, okay, where u I can think about is a function of z, and since z is a function of x and y, so if I change x and y, z will change, so I can think about u is a function of x and y, right? So if I change x and y, that means my z will change, and corresponding my f of z will change, that means w will change, that means my u will vary. So therefore I can think about u as a function of x and y, and u is I can think about is a map from R2 to R, because u is the real part of w, so it's a real valued function of real variable, two real variables. Similarly I can think about v, right? So as I said, so if z will change, my w will change. My w will change means u will change, v will change. So therefore v will change when z will change, and when z will change if I change my x and y variable. So in the same conclusion I can think about v is also a function of z, or we can think about v is a function of two variable x and y, because if I change x and y, my z will change, corresponding f of z will change, corresponding u and v will change. So therefore v also I can think about is a map from R2 to R. Why it's a range is R? Because v is the imaginary part of my complex number w, which is a real number. So therefore v is also a function from R2 to R. So in other words, what I'm trying to say is that each complex valued functions of complex variable I can break up into two parts of the form u plus iv, where u is a map from R2 to R and v is also a map from R2 to R. That is very important. So any complex valued functions of complex variable I can have this kind of form, u plus iv. Either if I have a functions, explicit functions, I can write what is my u, what is my v, or if I say that okay, so this is my u and this is my v, if I write u plus iv, it is a complex valued functions of complex variable. Okay, so this is very important. Why I'm trying to say, so later on you will see, so sometimes this, if I have a representation f, f is equal to u plus iv. Now next I will talk about the notions of what is called limit, notions of continuity, the notions of differentiability, right? Now look, so now one hand I have a functions f from, so now one hand I have a functions f from c to c, right? Complex valued functions of complex variable. Now once I have these functions, I will have this kind of form, right? So once I have complex valued functions of complex variable, right? So now if I write my f of the form u plus iv, now what is my u? Now u is a map from R2 to R and v is a map from R2 to R, right? Now you can guess, because see, when I will give the meaning of the concept of limit, continuity and differentiability, so now the question is, since f is the form u plus iv, where u and v are real valued functions of real variable, two real variables, but you know the concept of limit, continuity and differentiability of this kind of functions, because real valued functions of real variable or two real variable, so there you have the concept of limit, continuity and differentiability. Now the question is, when I will define or I will have the discussion of limit, continuity, differentiability, is there any connections? So that means whether the existence of limit of f will imply the existence of limit of u and v and vice versa. Similarly, whenever I am talking about the continuity of f at some point, will it have any impact on the continuity of its real part? So sometimes this u is called the real part of my functions and v is called the imaginary part of my functions f. So therefore if I have the concept of continuity, will it have any impact on the real part of my functions f, which is u, or will it have any impact on the imaginary part of my functions f, that means on the functions v? Or if I have the continuity of u and v, can I talk about the continuity of f? And similarly kind of differentiability. So that is why it is very important that once I have a complex valued functions of complex variable and it is, we can write as u plus iv, the concept of limit, continuity, differentiability, can I say in terms of u and v? And in later on you will see, yes, there is a connections. At least limit and continuity part, it will go parallelly. That means existence of limit and existence of continuity will imply the existence of continuity and limit of its real and imaginary part. That means it's on the functions u and v, and vice versa. That means if I have the existence of limit of u and v or continuity of u and v, it will imply the continuity or existence of limit of f. So it's vice versa. The problem you will kind of see in terms of differentiability. Differentiability, you will see there is a major difference will be there, and that is why what is called Cauchy-Riemann equation will come into the picture. Okay, so that is why it is very important to write my complex valued functions of complex variable of the form u plus iv, where u is a real valued functions of two real variables, v is a real valued functions of two real variables. Okay, so one examples I have given. For example, if I consider the functions f of z is equal to z square, so then I am saying that you can easily write. So what we have to do? See, these very simple functions. You have a z is equal to x plus iy, and then just do the algebra x plus iy whole square and just make it into two parts, real and imaginary part. Then it is real part, you can say that is a functions, it is the functions uxy, and imaginary part it is the functions vxy. So this is very simple. So you have so f of z is equal to z square, that means your w is z square. So that means sometimes, as I said, so real part of fz, which is u of xy, which is x square minus y square. So you can just do the calculations, right? So your w, which is u plus iv, right, one hand, and w is equal to z square, which is x plus iy whole square, right? And you do the algebra, so you can do that. So what is that? This is x square minus y square plus I times twice xy, and this is the portion u part, and that's I have written u of xy is x square minus y square, and this is the portion v of xy is equal to 2xy. So therefore my f will have a representation u plus iv, where u is a function of two real variable uxy, which is nothing but x square minus y square, and v is nothing but this. So this is very simple, that's why you can write it, but anyhow you can have the representations. That means if I have a complex valued functions of complex variable, then I can write it is of the form u plus iv, where u is a map from R to 2R, v is a map from R to 2R. Okay. Okay, this is like visualizing our complex functions. So in order to investigate the complex function w is equal to fz, it is necessary to visualize it. We view z and its image w as points in the complex plane, so that f becomes a transformations or mapping from the z plane, that means the xy plane, to the range R in the w plane. So therefore this is my functions f. So in the left hand side I have a domain, that is the z plane, that means our xy plane. Image is the w, which I am writing as u plus iv, which is in the uv plane. So therefore you can think about this map fz, it maps the point z to w, that means it maps from z plane to w plane. So suppose this is my domain in the z plane, then the corresponding range it is lies in the w plane. So that's my notation, this is the visualizations. So in order to investigate a complex function, it is necessary to visualize it. So therefore whenever I am talking about point z in the domain, that means z I can have the notation as x plus iy, that means I am in the xy plane. And what is the image? Z goes to f of z, w, and w I am writing as u plus iv, that means I am in the uv plane. And if I take a domain in the z plane, its range is in the uv plane. So that is the visualizations. Okay. Okay, so I think I should stop here. Till now I have discussed like the remaining topological concept I have discussed, and then I have like introduced the definitions of complex valued functions of complex variable. Then I said that each complex valued functions of complex variable I can write it of the form u plus iv, where u is a map from R to 2R and v is a map from R to 2R. And this is the corresponding visualizations of a complex plane. That means it is domain is in the z plane, range is in the w plane. So now next lecture I will talk about the concept of limit and continuity, okay, and then we will see how the concept of limit continuity, of course the concept of limit continuity you know in from functions of real valued functions of real variable. You will see parallel kind of definitions I will have in the context of complex planes. So that is one observation. Another observation is that, so that concept of limit and continuity, can I have any impact on the real part of f and imaginary part of f, and vice versa. So those kind of concept I will discuss in my next lecture. I think I should stop. Thank you.